Alright, metallic bonds. Kind of sounds like metallic bands, like Metallica, but it's not. Sorry if I got your hopes up. Okay, metallic bonds. Last one of our three, right? We already looked at ionic, we looked at covalent, now we're looking at metallic. So already, I'm thinking metallic must have to do with metals. It's right in the name. So metals behave very differently than ionic and covalent compounds. They conduct electricity in the solid state, meaning electrons can flow through metallic bonds without disrupting the compound structure. Now, ionic does it when dissolved or melted, but a lot of times it's not useful because you can't like build a wire out of a melting something. That doesn't make sense. If the compound structure is changed by bending or twisting a metal, the metallic bonds are rearranged and the metal stays together. So this is why metals are malleable. Metals are essential to modern life and have found uses in electronics, structural engineering, transportation, cooking, and many other areas. Electrons are not very tightly bound due to metals' low electronegativity, right? That's attraction to electrons and ionization energy. In a metallic bond, the valence electrons leave the metal and wander around through the metal. Because electrons are not locked into one specific area, they are sometimes called delocalized. So delocalized means not local, right? They can go wherever they want. Or a sea of electrons, right? They're everywhere at once, and it's like the cations are like the boats. When the metal atoms lose their valence electrons, the metal atoms become positively charged. So that means they become cations. These metal cations are attracted to the delocalized electrons through electromagnetic forces, forming a metallic bond. So what's this showing? Metal atoms lose valence electrons easily because of their low ionization energy. So these electrons lose and they become delocalized. So here the electrons are just everywhere, and the positive cations now are just stuck inside of them. The mobility, so the movement of the valence electrons, leads to metal compounds' characteristic properties. Electricity is simply electrons in motion, or any charge really, and metals always have delocalized electrons which can move around. When a metallic compound is bent, the metal cations are still always in the sea of electrons and remain bound together. This is why metals are malleable and not brittle, right? Whereas an ionic compound, right, if you have positive, negative, right, this is the crystal lattice, right? And if you bend this, let's say you take this and you, so now you have positive, negative, positive, and now you take this and you rotate it, now you have positive, negative. Well, these are going to repel, right? And so it's not going to stick together. Whereas the metal is always in the sea of electrons, so it's always bound together. So here are those attractive forces here. So the nuclei attracts the electrons, and these electrons are all moving around, right? But the positive cations are just attracted to everything, and so they stay bound together in these metallic bonds, which are stronger than covalent but weaker than ionic. Very interesting. So we still have ions, but it's not exactly ionic because there's no anions. There's just cations and these electrons. Cool. So now you know all three types of bonds. I'll see you in class.